Oxidation and Combustion, a short essay by Bruce Mills, otherwise known as the Obligate Pedestrian. Viable theories of the microscopic nature of materials have been difficult to construct. Contrast this with the theory of macroscopic nature of materials, such as the orbital mechanics of the solar system, which was very much a product of the 1600s, for example of Tycho Brahe and Johannes Kepler and Isaac Newton. From the late 17th century to the early 19th century, the study of the motion of the planets was mostly mathematical work based on the rules laid down by Kepler, who worked out the inverse square law from doing data analysis on the data provided by Brahe, and then given a more rigorous mathematical treatment by Newton. In the 1600s, Leymery, Boyle and Freund, among others, attempted to lay down a small set of axioms for material behaviour along the lines of Euclidean geometry, at least partly inspired by the work on orbital mechanics that turned a large set of disparate but direct observations into implications of a very simple set of axioms from which rigorous work with material implications could productively flow. Compared to the success of orbital mechanics, the study of the orbits of the planets and moons in the solar system, the success of atomic theory was abysmal. The phrasing of Newton's laws of motion is short and crisp and accurate and leads to so much detailed mathematical development. The laws of atoms, as given in the 17th and 18th centuries by Newton in Optics, Query 31, Leymery, Boyle and Freund, were badly stated and ambiguous. At best, they allowed some vague qualitative reasoning that was, for the most part, worse than the earlier theories of essences and principles. I wish to coin a term here. In keeping with the distinction between analytic and synthetic geometry, there is analytic and synthetic chemistry. René Descartes, 1596 to 1650, developed the principle of describing all of geometry in terms of algebraic relations between coordinates and converting all the problems to algebraic problems, based on the property of the real numbers. This was a shift from the ancient Greek geometry, which was then termed synthetic, meaning something like geometry that assumes the existence of something that one is going to give axioms about and deduce behaviours from those axioms. There is some ambiguity in this definition that I won't try to clear up, but the basic idea informally is that in synthetic geometry one assumes the existence of the plane and deduces properties of numbers from that, and in analytic geometry one constructs the plane in terms of those numbers, so the analytic plane is literally pairs of real numbers. Up until around 1930, chemistry was synthetic. There was a list of materials with properties assigned to them and a huge body of ambiguous definitions and laws about combustion, oxidation, acids, bases, and so on. From 1930 on, there was a notion that atoms satisfied differential equations. The theory could be described in terms of analytic geometry. Definitions then started to be made in terms of the details of those solutions to those equations. Things such as orbitals are very much a feature of the quantum theory, which is an analytic theory and not a direct feature of laboratory or synthetic chemistry. The synthetic theory of microscopic rules of materials is much more complicated than those of orbital mechanics or even of geometry. There is a great deal of ambiguity and circularity in the definition and axioms. Things are just so, except when they are not. Many laws are not so much laws as points of view from which to judge things. Classifying by its elements does not define the material due to the existence of allotropes and isomers. It is often claimed that the law of definite proportions, that substances can only form from a definite ratio of definite elements, rules. This is the core of the theory of stoichiometry. The law of definite proportion states that any specific chemical compound always has components in a fixed ratio that does not depend on how it is prepared. Water is always one atom of oxygen to two of hydrogen, although that would originally have been specified in terms of ratio of weights. This law was stated by Precis as well as Lavoisier, but is often ascribed to Joseph Proust in 1797. This is sometimes said to be obvious to modern chemists, but things are not always that simple. Substances that do not conform are just called non-stoichiometric compounds. For example, iron can have oxidation states of 2+ or 3+, leading to ferrous and ferric compounds. Some materials do not even have any definite proportion. For example, when an element might randomly use one of multiple oxidation states within the body of the material. The law of definite proportions is not really a rule, but rather a classification. There are things that obey the rule, and things that do not are said to be unlawful, in some sense, but still exist. The law is correct only when it is correct. They are anomalous, but only if you take the view that the law is given. Everything is either an acid or a base, except when it is not. This generalizes to everything has a definite position on the spectrum of acid and base, perhaps measured by pH in solution, except when it is amphoteric. The success of modern chemistry is not in its correspondence with some deep truth. The truth is that we do not know what the truth is. The success of modern chemistry is in its contextual utility. We tend to judge other theories to be wanting simply because they do not agree with the implied ontologies of our own theories, but we do not know that our ontologies are correct, only that they are ours. The more objective measures of theories is whether, or rather to what extent, they work in practice and in context. The analogy that I often draw on for my own understanding of this is French versus English. The fact that the French words do not correspond one-to-one to the English words does not mean that French is lacking as a language. It does not mean that the French way of expressing things is incorrect due to different cultural presumptions. The term oxidation is said to have originated with Antoine Lavoisier, 1743 to 1794, who was executed within the context of the French Revolution in the late 18th century. This makes some sense since Antoine Lavoisier invented the word oxygen, in the erroneous belief that all acids contained oxygen. Humphrey Davy demonstrated that not all acids contain oxygen only a few years later, but after Lavoisier had been executed. Oxidated begins as a concept of having been combined with oxygen. It was not really a new concept once oxygen was admitted. The word is a derived one. Similarly, phlogisticated meant having been combined with phlogiston. The distinction is only that the one uses oxygen and the other uses phlogiston. One might claim that phlogiston did not exist, but that's another matter. The linguistic construction is the same. However, what is meant by oxidation in the early 21st century is rather different from what was meant by oxidation in the late 18th century. In the 21st century, oxidation is the sharing of an electron, and that is really a quantum chemistry concept. The idea of the electron might have been coined by Richard Laming circa 1840, who proposed the idea of an atom being a core of matter surrounded by subatomic particles. This was followed by Stoney, who suggested quantization of charge. Thomson famously isolated electrons in a cathode ray in 1897. However, in none of this was there a definite idea that bonds between atoms came from sharing electrons. Gilbert Lewis, 1875 to 1946, is often credited with the electron bond idea in a paper published in 1916. This arose from the valence theory, which predated the quantum theory of orbitals. This led Lewis to define an acid as a material that could accept an electron, and a base as something that could donate one. At a basic level, all the way from Thales, circa 500 BC, the idea is to find a set of prime materials from which all the infinite variety of materials that one finds around in the world are derived as allotropes and mixtures. The word mixture has also changed its meaning. Earlier it meant closer to what in the 20th century is meant by the word compound. Pseudo-Geber, 1305, in Summa Perfectionis, mentions the idea of strong and weak mixtures. However, these seem to mean something closer to, again in 21st century terms, the idea of a chemical combination and the idea of nuclear binding, as of protons and neutrons. Oxidation was coined in the late 18th century. In the 19th century, much work was completed on identifying a good set of prime materials. The prime materials are identified essentially by the relative ease of breaking apart materials into the prime materials, for the most part using fire. However, electricity was also required in some cases. The original idea of breaking apart was to heat a singular material such as wood and to collect the different materials that resulted. The different materials were then closer to being prime than the singular material. Some people took it as axiomatic that the materials produced by a really good furnace were prime. This was complicated by some failure to account for combinations with air in the process of burning, and perhaps also the failure to capture airs that were let off during the burning process. But the basic idea had a point. Later in the 17th century Europe, for example, the same kind of processes were conducted by heating inside a sealed glass container that might even have been evacuated after the invention of the vacuum pump. However, looked at from a 21st century point of view, enough photons will cause atoms to break apart and reform. So in a particle accelerator or the core of a star, one could have a reaction in which oxygen and heat leads to beryllium and a reaction in which beryllium and heat leads to oxygen. Neither are prime at that level. Even if one subscribes to the atomic theory, if one does not know how to count the number of particles, it is not possible to determine whether oxygen is composed of beryllium, in the nuclear sense, or beryllium is composed of oxygen. It is partly the difficulty of splitting at the nuclear level that makes chemistry work. Breaking apart could be identified by the principle that if a reaction involved two reactions and one product, then the product was not a prime material. The Chambers Cyclopedia was published in 1728, while Lavoisier coined the term oxygen around 1790. Hence, Chambers does not mention oxidation, although it is interesting to note oxycrate, which is a pharmaceutical mixture of water and vinegar. I take that to mean dilute vinegar in the 21st century terms. And oxycrosium, which is a saffron and gum dissolved in vinegar, as well as oxygala, which is sour milk, which in diluted form is said to be a popular drink with the Turks. Oxygonious means acute angle, that is, sharp, and oxymel is honey and vinegar, the shared root meaning sweet drink with mead, and going back to Indo-European roots, oxymel, sweet and sour. It continues with the vinegar theme. So Lavoisier using oxygen for acid maker was almost not even a coinage but a standard principle of use. Chambers does not make any mention of phlogiston either, as that was coined as a principle of scientific theory of combustion in 1723 by George Stahl, and presumably did not make it to the attention of Chambers as part of the then modern science. Chambers also does not mention terra pinguis, the earlier term used by Stahl's mentor Becher. Becher did not really construct the phlogiston theory, although his work inspired Stahl. Page 805, Chambers, Volume 2. Phlogosis. In medicine, a degree of the ophthalmia. When the inflammation of the eye is light and gentle, it is called a phlogosis. When very severe, chemosis. End of quote. Phlogiston as a word meaning something like principle of fire seems to have been around since the early 1600s and was used rather than coined by Georg Stahl when he introduced his phlogiston theory of combustion in Zymotechnia Fundamentalis Chemia in 1723. It is sometimes said that it was obvious that combustion did not involve release of combustion products because substances that burned in air would not burn in a vacuum. However, the principle at the time was that the phlogiston had to be absorbed by something else. It would not just move into the vacuum. Hence, air, for example, was moderately good at absorbing phlogiston, but would eventually become saturated. This might be phrased as saying that the vacuum was actually full of phlogiston, which could not be removed by a vacuum pump, just the opposite in fact, as matter would lower the density of phlogiston. In 21st century terms, the fire stopped because the oxygen was used up. In the 18th century phlogiston terms, the air would not absorb any more phlogiston. If one essentially identifies oxygen as being a place where the phlogiston can be put, then it is clear that the two theories are not at all easy to separate based on the experiments available. Combustion in a modern chemical dictionary means complete oxidation. In some sense, the word is rather like the older use of calcination. On the other hand, the 17th century definition seems to have been closer to a spontaneous chemical process that emits light and heat. Some sources say that combustion is oxidation of hydrocarbon. Urey, A Dictionary of Chemistry and Mineralogy, page 353, 1831. Combustion. the disengagement of heat and light which accompanies chemical combination. It is frequently made to be synonymous with inflammation, a term which might be restricted, however, to that peculiar species of combustion in which gaseous matter is burned. Ignition is the incandescence of a body produced by extrinsic means without change of its chemical constitution. And a couple of paragraphs later, Stahl adopted and refined on the vulgar belief of the heat and light coming from the combustible itself. Lavoisier advanced the opposite and more limited doctrine that the heat and light proceeded from the oxygenous gas in the air and other bodies, which he regarded as the true pabulum of fire. Stahl's opinion is perhaps more just than Lavoisier's, for many combustibles burn together without the presence of oxygen or any analogous fancied supporters, as chlorine and the adjuncts to oxygen have been unphilosophically called. Sulfur, hydrogen, carbon and azote are as much entitled to be styled supporters as oxygen and chlorine, for potassium burns vividly in sulfurated hydrogen and in procene, and most of the metals burn with sulfur alone." End of quote. Combustion, in that sense, is not specifically combination with oxygen. I think the correct interpretation of the intention of the word unphilosophical in 21st century English would be closer to unscientific. In retrospect, one reason for going with oxygen rather than phlogiston is that it is possible to construct a bottle full of oxygen that obeys the ideal gas laws. That is Avogadro's law from the 19th century. It states that equal volumes of gases at the same temperature and pressure have the same number of molecules. As with most such laws, this is not inviolable. If a gas does not behave this way, it is said to be supercompressible. The law was stated by Amedeo Avogadro in 1812. It gives a reason to use oxygen rather than phlogiston, as the phlogiston gas laws would not be the ideal gas laws. That is not to say that one could not produce phlogiston gas laws, but it would be more regular to use oxygen. To see that in terms of phlogiston has to be a pervasive substance, and the holes in the phlogiston, which effectively would be oxygen in all but name, would be the more important component. It is important to note that the electron hole theory of semiconductors has exactly this structure, where electrons are pervasive, and so the interesting feature are the places where they are not, the holes. At the top of a conduction band in a semiconductor, an electron would have negative mass. Hence, replacing this with a positive mass particle of positive charge, the hole, is often considered more intuitive and simpler to analyze. In this case, the hole theory is said to be an effective theory rather than the fundamental theory. The fundamental theory is that the conductor is full of electrons. The effective theory is that there are a few holes, which are gaps in the electron C. The distinction, however, begins to feel to me to be dogma rather than measured behaviour, so I avoid almost all these ontological questions. It is curious that dogma used to mean, in ancient Greece, that which seems true. Then it became that which is absolutely true in religion, and from there took on the meaning that which is demanded without justification to be true. The theory of matter and antimatter had a similar impact. In its first formulation, antimatter, such as positrons, were interpreted as being holes in the sea of electrons. This idea was proposed by Paul Dirac in papers in 1928 and 1931. Initially, the idea was of holes, as is used in the electron hole theory, but it was modified to conjugate fields, so the positron exists in its own right, rather than just as the absence of an electron. Although recent experiments have suggested otherwise, it has been conjectured that positrons, as well as having a positive electric charge, might have a negative gravitational charge. Give an example of matter that has a gravitational charge that is not the same as its inertial mass. While this does not seem to have panned out, and most particle physicists bet against it, it was not an idea that could be dismissed out of hand as logically or physically absurd. Getting back to the 17th century, Johann Heinrich Pott, a student of George Stahl, gave an axiomatic version of phlogiston theory that had much in common with the atomic theory of Newton, Lemery, Boyle and Freund. However, he said that one could not pick out particles of phlogiston, and that rather it was an essence that permeated all materials to a lesser or greater extent. Phlogiston is a circular movement. 2. When homogeneous, it does not participate in combustion. 3. It often causes expansion, but the mechanism is unknown. 4. The increase in weight during calcination is most likely due to contamination. 5. Air can absorb phlogiston. 6. It is the active principle of inanimate bodies. 7. It is the basis of colours. 8. It is the agent of fermentation. Potts, 1692 to 1777, was active until the 1760s and died in 1777. This is getting on towards the advent of oxygen theory. Guillaume Francois Rouelle, 1703 to 1770, was a popular French chemist who introduced the idea of phlogiston to France and became very popular. He is considered responsible for the introduction of the concept of base into chemistry. One of his students was Antoine Lavoisier. In the mid-1700s, phlogiston was accepted in France as some form of essence that could not be isolated but permeated all substances. The myth of Lavoisier is that he heard of the phlogiston theory in the late 1700s, principally as given to him by the British Joseph Priestley, and then he sat down in his laboratory and realised the theory was nonsense and put forward the correct theory of oxygen. In fact, Lavoisier, a student of Rouelle, would have learned and used the phlogiston theory and been familiar with the principles. The matter of the existence and nature of phlogiston was complicated, and it covered concepts of the composition of water as well as the idea of combustion and of acids. Lavoisier stated that all acids provided oxygen. Cavendish said that acids provided phlogiston, but identified phlogiston with what is now called hydrogen. The concept of phlogiston was part of an ongoing discussion as part of the first really solid attempt at a unified theory of chemistry. The various enigmatic behaviours of phlogiston were eventually separated out and explained separately. The principle around was that a metal is a calx combined with phlogiston. The fact that a metal calx is heavier than metal was known before Lavoisier. Lavoisier did not invent the idea of checking the weights, nor was this fact seen as a terminal problem for phlogiston, at least not immediately. It did, however, modify phlogiston from a particle to a principle, which, as mentioned above, led the way to oxygen being introduced as holes in the phlogiston field. Another problem for phlogiston, noted at the time, was that a more detailed analysis of the situation showed that phlogiston, being lighter than air, would not explain the calx being heavier than metal. However, the more correct version of this was that the gravitational charge of phlogiston would have to be negative. In modern terms, it would have to be exotic matter. As noted above, this could alternately be phrased as the universe being awash in a sea of phlogiston and the holes in that sea being the active principles. Andrew Urey, Dictionary of Chemistry and Mineralogy, page 678, 1831 edition, phlogiston, the supposed general inflammable principle of style, see combustion. Phlogisticated gas, nitrogen or azote. Phlogisticated alkali, prussiate of potash. End of quote. Andrew Urey, Dictionary of Chemistry and Mineralogy, page 673, 1831 edition. Oxidation, the process of converting metals or other substances into oxide by combining them with a certain portion of oxygen. It differs from acidification in the addition of oxygen not being sufficient to form an acid with the substance being oxidized. Oxides, substances combined with oxygen without being in a state of being an acid. Oxygen gas. This gas was obtained by Dr. Priestley in 1774 from red oxide of mercury exposed to a burning lens, who observes its distinguishing property of rendering combustion more vivid and eminently supporting life. End of quote. Note that Priestley here is given credit for discovering oxygen. There has been some contention over whether Priestley or Lavoisier should be given this credit. Scheele is said to have discovered it independently, but Michael Sendivogius, 1566 to 1636, isolated a gas before 1604 that clearly seems to be an oxygen. He called it the food of life. For modern sources, as a broad approximation, metallic oxides are basic and non-metallic oxides are acid. However, there are metallic and non-metallic oxides that are amphoteric. The oxide ion is a very strong basic ion due to its small size and high charge. The hydroxide ion is the strongest base that can persist in water. The oxide ion reacts with water to generate hydroxide ions. O plus H2O is 2OH. The trick seems to be that in one case the combination with H2O binds OH strongly, leaving an H flapping around, perhaps so much loose that it forms hydronium with some other water molecule. but in the other it binds the H more strongly, leaving an OH flapping around. Humphrey Davy in 1815, about 20 years after Lavoisier's oxygen theory, suggested that acids had a replaceable hydrogen atom. This is very close to the proton donor theory or definition of acids. When acids react with metals, they form salts and hydrogen gas, and this is partly circular in that once a theory of generic reactions is broadly accepted, participation in those reactions becomes part of the process of classification of chemicals into kinds. Keep in mind the changing definition of acids. Acids start as being sour, alkalis are bitter. The test of turning syrup of violets red is recognised in the 1600s, but a true acid is said to taste sour, while something that turns syrup of violets red but does not taste sour is a dubious acid. One question involved in the oxygen phlogiston debate is, what is the nature of water? Is it a compound or a prime material? Is water actually H2O? In Zumdahl, Introductory Chemistry, a chemical change is described as a process in which a fundamentally new material is formed. Examples are given of water changing steam, a physical change, and water changing to hydrogen and oxygen gas, a chemical change. But this is not really something that we observe directly. Water is a combination of hydrogen and oxygen. To separate it out into hydrogen and oxygen gas rather than steam is seen as a chemical change simply because it is claimed that in the water, in the theory, the material is made from the molecules of water. However, within our current understanding, this is not really true. There are clumps of hydrogen and oxygen in a ratio of 2 to 1 that form, but there are also hydrogen and hydronium ions, and there are weak bonds between full water molecules, organising them into larger lattices of molecules, and practical water might have hydrogen and oxygen gas dissolved in it. The selection of water as being H2O molecules is not really justified. The pH of water is literally defined in terms of the extent to which water is not just H2O molecules, but is also hydrogen and hydronium ions. The argument at the end of the 18th century over whether water was a prime material or not is curious in that practical water has many impurities in it, so the issue was not so much one of whether water was a prime material, but what prime material did practical water have in it, and the selection of the most common one to be called pure water. Hence, the process was not one of purifying water as deciding on what material should be called water.